Okay. So this week's problem, container with the most water. So this is, I think, sort of conceptually, this problem is relatively easy to sort of just understand the basics of it. But I think, right, we're going to get into the weeds here is going to be the algorithm for this. So it says you're given an integer array height of length n. So there are n vertical lines drawn such that two endpoints, right, of the ith line, I0 and I of this height. So find the two lines, and I think it's just easier to visualize this. So you have an array with numbers. Numbers represent heights, right? And so they say find the two lines that together with the x-axis, so you've got width and you've got height, that together with them will form a container such that the container contains the most water. And then it says specifically, return the maximum amount of water a container can store. And then it just notes you may not slant the container. Okay, that's an important thing, because if you slanted it, arguably you might be able to just choose. Yeah, so right, so I guess visually very easy to sort of see this represented here. You have input heights here. On one end you have 8, the other end you have 7. And then in this case, the output here, so it's going to be 7 height, and this is going to be 7 width, so it's going to be 49. So, yeah, constraints, n is equal to the height length, so length of it, right? There's maximum, there's ultimate size to it, and ultimate size to the height. So there's some varies in terms of how the size of the array and the size of the height. Okay, so I'm kind of curious. Did anyone have any thoughts as to how to go about doing this?
I did 2 for loops,
Mm-hmm.
nested for loops.
Okay, good, perfect. And actually, that I'm glad, because that's where I wanted you to start. So, and that's what we would call the brute force method, right? The idea being you take an outer loop, which takes each of these, and for each of these, just calculate, okay, say, okay, well, what's the volume of water between these two, and then these two, and then these two, these two, these two, these two. Okay, what about this one, 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 right? And just store max and return max, right? And theoretically, if you code that up, that'll work, right? I don't see any reason why that wouldn't work. And that's probably the intuition, right? That's what we would think of when we think of as a brute force thing. We say, look, just calculate every possible permutation of, two poles and the associated area between them, and just store the max. Right? Now, anybody knows, going back to our O of n thing. So O of n being, again, n being the size of the data set, what that runtime would look like.
N squared.
N squared, correct. Okay. And so, again, for those still kind of getting the feeling for that, O of n squared basically says it's n times n, which means for each element in your array, it interacts with every other element in the array. So again, it's not precise, right? Because remember, these are orders of magnitude. But yeah, it's O of n squared, exactly, because each n is interacting with each of these elements is interacting with n other elements, right? This one is interacting with everything else. This one's interacting with everything else, and so on and so forth. And so, yeah, so an O of n squared for that. Okay, so again, so we can sort of code that up. We can sort of get that running. The question is, can we do this a little bit better? And specifically, can we get this down to an O of n runtime? And when we talk about an O of n, essentially we're saying that we basically loop our data set once, and by the end of that data set, by the end of that loop, we have the solution. That's sort of what we're going to aspirationally shoot for. And probably the biggest sort of paradigm for doing so is sort of an algorithmic approach that we call greedy. And again, this is something like we spend a decent amount of time if you take an algorithms course on it. But here's sort of the essential idea. When you loop through, the way sort of a greedy algorithm can be constructed is when you sort of loop through your data set, you're able to do a handful of really basic local calculations. And based on that, you make a decision with the best of knowledge that you have on hand. So that's when the idea of choosing something greedily is, right? We don't wait until we have global understanding. We just say, based on what we've seen up until this point, this is the best thing we've got. And you have a really basic sort of organizing principle, something that as you're looping through, you can sort of calculate for each n. It's sort of a fixed set of operations per input. Allows you to make a decision. Each time you're able to say, here's what's best, here's what's optimal up until this point. And then the idea is that when you have run the program to conclusion, when you've done O of n times, what is left is the optimal solution. And I will share some, again, I'm going to, I'm not going to put this into the formal course because this is very much not Python stuff, right? It's important from technical interviews perspective. So I will share this material. But I'm not going to belabor it because it's obviously not Python stuff. But, and in the material, like we talk a lot about just like ways in which to do this. And then here, I think I have sort of a nice summary of it here. So again, the three element, right? So to understand about greedy. And again, right now, this is all conceptual, right? Right now, we don't have you don't have a practical understanding of what that means. So bear with me. We're going to get into the practicalities of it. But the key thing to remember greedy, right? It's not global. You're not running an exhaustive thing. You're just looping through your data set. You're doing local, which means sort of a fixed number of operations based on the limited information that you have on hand. And that structure will, by the time it's run to completion, result in the ultimate answer. That's right. So basically the three elements of a greedy thing, you will conduct sort of a limited fixed analysis. You, for each analysis, you make a decision based on what is the best up until a point, right? That's the greedy aspect of it. You're always making a decision. And then the idea is once you've cycled through your data once, you will have arrived at the optimal solution, just going through that. So, and so in a moment, and so we're going to sort of talk through this because we're going to talk through, a sort of a greedy approach to this. And then, but then the critical thing about this is we're going to talk about how to prove it. Because the key aspect to sort of making greedy algorithms work is this idea that there's a pattern. There's an organizing principle that your algorithm is going to be based on. And as long as you follow that organizing principle, whatever that is, it will lead you to the correct solution. Okay. So I'm just going to, again, because, and right, this is a very different way of thinking about it. So here's the greedy algorithm that I took for this. I basically said, okay, and again, I think this visual is actually really helpful just having this up here to look at. But start with the two ends and compare the height. And then I say, whichever end is lower, increment that to the next one. So if I start between this one and this one, increment here. Then recalculate what this height is. And then I see, okay, and then as I'm going along, I just run a counter that says, okay, what's best? And then I run that same thing. I say, okay, well, which one is lower? This one is lower. Okay, go here. This one is lower, go here. This one is higher, go here. In this case, these might be equal, so I may have to do an edge case there. I didn't actually do an edge case, I realized, but I guess it worked out. Calculate, calculate, calculate. And then once I'm done, I return whatever's best. And the key thing here is if you think about the number of, so how many potential comparisons am I making there? If you think about it.
Or it's still,
Well, with each one of these, basically, I'm going to be sort of moving the pointer once. It's O of n, basically.
oh, and there's a 10.
Right? Because if you look at here, I'm making this comparison, then I'm moving one pointer over, then making another pointer, then moving another pointer, another pointer, another pointer, another pointer, another point, right? Until they're equal, and then I stop. And so for each of those pointer moves, I'm doing a comparison. So I'm not doing exhaustive, I'm doing a pointer move. And my basic argument is that by doing that, I can guarantee that the optimal one is going to be there. Now, you guys aren't convinced yet, and you shouldn't be yet, because I have not done the work of explaining the organizing principle, nor have I proven this to you yet. So here's the organizing principle. The organizing principle says, when I'm looking at what's going to impact the height, right? I have two ones. I have left and right. Which one impacts the height?
The lowest one.
The lowest one, right? So the lowest one, so I can only improve by potentially shifting the lower one in, right? By changing the lower one, because this, I already have excess capacity here. Moving off this one isn't going to help because this is the rate limiting one. So I can only potentially go up by moving this one. And so that's why I'm going to say my organizing principle is always to go in further, in. And the reality is, by going in, right, I'm also shrinking the width too. It gets smaller every time I do that. So I know every time I go in, I want to go in by the one that can improve it, not the one that is already, if I already have wasted capacity, at best, it stays at that level. At worst, it goes down, right? So if I'm going to go in, I need to go in with the idea of improving. So that's the organizing principle. So that says, by using that basic rule that says, move the pointer based on which of the two is the current limit, the height limit, will give me potentially the optimal mix. Okay. So sounds reasonable, right? Maybe. But how do I actually know that's true? Conceptually, how do I know it's true? And this is, again, this is sort of the part of what, like, if you're in an algorithms course, what you really emphasize is this is where proving your approach is so critical. Because, right, you have this organizing idea, you have this organizing principle that says, move the pointer based on the rate limiting thing. Seems logical. How do you work it? How do you prove it? So, and there are different sort of ways of thinking about this, and I apologize, guys. I'm kind of giving you like a little bit of a crash course on intro to algorithms. But the easiest, probably the most intuitive way to prove something is what we call a proof by contradiction. And the idea says, if I want to prove that this always works, right? If you think about logic, there's a thing that says, if something always works, there is never an instance where it doesn't work, right? And because if you think about it, it's much easier to prove that there is never an instance of something than to say something always works. So proof by contradiction says, assume my algorithm fails. Assume that I returned a result, but my algorithm did not work. It missed an actual superior thing, right? Assume that that's the case. And then what a proof by contradiction shows is you say, okay, well, let me break down the structure of the algorithm and talk mechanistically how that mistake could have happened and show that it's impossible for that to have happened. Right? Which is it takes an abstract thing and basically says, assume that my algorithm has failed. Here's what a failure would have looked like, right? Be very concrete. Here's what a failure would have looked like. Here's why that failure is impossible. So using our own example here, let's assume, right, if this has failed, if my algorithm has failed, right? So remember, my basic approach says, take my 2 pointers, whichever one, right, calculate the volume of that container, take my 2 pointers, whatever's the smaller one, move that pointer. Recalculate, see which is smaller, move that pointer, recalculate, move that pointer, recalculate, and so on and so forth. Okay. If my algorithm fails, that means, more precisely, I moved the wrong pointer, right? I moved right when I should have moved left. I did it in the wrong order. And because I did it in the wrong order, I missed a more optimal approach. Right? So you see, that's because when I define the mechanism of my algorithm, then I can also define what it means for my algorithm to fail. Because I have a very precise thing of how it works. So now if it fails, here's why it fails. Here's how it must have failed. right? I moved the wrong way. And now that I have that basis, I say, well, if that, and now I can say based on the logic of my algorithm, is it possible that moving a different way would have produced a better outcome? So in this case, right, so my assertion is, no, my algorithm doesn't work. My algorithm missed something. I moved right when I should have moved left. If I had moved left instead, I would have gotten a better outcome.
But that's not true.
It's not true though. Why? Because, and this is where this is the sort of the proof by contradiction. It's not true though, because my entire basis is the only way I can improve the height is if the lower bound goes up.
Yeah.
Right? It doesn't matter what happens with the upper bound. Moving this at best gives me the same height, but at a lower width. So at best, it's going to come in under. At worst, it comes in way under. And suddenly I lose even more head capacity. But so there's no way that if I was supposed to move right and I moved left, there's no possibility that that solution could be better. The only way something could be better is if I move it the way my algorithm says, right? So again, which is going from like, so in this first instance, if I start at these two on the ends, so the only way to improve it, so right at that point, it would have been this very small thing. Moving here dramatically improves it. Moving here does nothing, right? I'm still, this is height limited. All I've done is made it less one. And so by arguing from the mechanics of it, I can say there is no way my algorithm does not produce the optimal that way.
Oh.
So that's how you take sort of an abstract idea and you can kind of and make it concrete.
And so your algorithm is gonna keep on running until both pointers meet in the middle?
Yes. Okay. So
Okay.
now that we have sort of the basic idea. Let's talk about the actual structure of the algorithm. So the algorithm says you initialize. You have your left pointer, your right pointer, and you have your best thing. Because remember, what we're returning here is the area of the algorithm. So you start out, so you do, in this case, like I did a while loop. And I say, okay, while left is less than right. So while they're still apart, calculate the current, calculate current volume, which is the minimum of these two pointers times the distance between them. Calculate that volume, compare it to the current best. If it's better, update. If it's not, keep the current best. And then, whichever one is less, increment. So if the left-hand side is less, increment up by 1. If the right-hand side is less, decrement by 1. Recalculate, update if necessary, then decrement, right? Recalculate again, increment, then decrement, then increment, and then decrement, and then your while loop terminates, and you return your thing.
And question, I know that
Yeah.
based off, I'm assuming the test scores didn't have like where two values were equal, but how would you account for that? So
Yeah. So if they're equal, you could just kind of you could hard code a if equal increment type deal, because at that point, it doesn't really matter which one you move off of.
okay.
You would, because if they're equal, again, right, it doesn't really matter. You can move off either of those.
Oh, and then either way, that's gonna eventually lead, even if the right side doesn't move after that, the left side will eventually meet to the right side.
Exactly.
Oh, okay. That makes sense.
Okay. So
But this way, you only have to do this all in because you're only doing it like 10 times instead of doing it like 100 times.
exactly. Because using this organizing principle, right, you can say every time I'm going in, I have less width.
Yeah.
So the only thing that can help is if my lower bound increases dramatically enough to offset that.
Yeah.
And so once I figure out that organizing principle, I basically just kind of loop along that. Okay, so let me pause there. Do you guys want to take a few minutes to try and code that up yourselves? Okay, cool. So, all right, so let me pause recording. All right, okay. So again, I'm going to start So I'm going to initialize kind of just a few things. So left, right, left-hand side, I'm going to start with the index. So I'm going to start here. Left is 0. Right is going to be, so I'm going to do the length of, so our input's going to be height. And of course, -1, right? Because the whole indexing, so the farmost index is just length -1, right? All right. And then I'm going to basically get a score here. So I'm going to say best. And right now, best is going to be 0, right? So when I'm initializing it, right now I haven't calculated anything yet. So I'm just going to start with that. Okay. So my overall while loop is basically going to just be as long as there's a gap between left and right, right? As long as there's a gap here and here, we aren't all together, there's still something to calculate. So while left is less than right, so right, because the moment that they touch each other, nothing left to calculate, nothing left to see. So as long as that's the case, okay. So the first thing is I have to, in order to calculate this, I have to decide what the height is going to be. So in this case, the height is simply going to be the minimum of left and right, right? So in this case, I'm going to say left is, to make it clear, I'm going to say, I'm going to call the variable tall just to specify, because I can't say, because we're already using height, and so I don't want to reuse height because height's the overall list. I'm just going to call it tall. I call it length. No, that's going to get confusing because we're using length as well. So no. Okay. So I'm just going to say tall equals minimum between, and now it's going to be either height left and height right, right? So that's going to be, you're going to take the minimum of those two values. You're going to put those two values in as inputs, and then you're going to return the minimum. And that's going to be the tallness, or the height of that. And then our area is just simply going to be, right? So area is just simply going to be equal to tall times the width. And the width here is simply difference between right and left, right? It's going to be a difference between them. Okay, so now I've calculated area. So based on that, I'm now going to say if area is greater than best, then best equals, yeah, right? So if it's beaten the current thing, update it. If not, don't. And again, no need for an else block there because only if it's better do you update it. If it's not better, no point in touching that. Okay, so that handles the logic of calculating it. Now we need to handle the logic of, so we're almost done. We just now need to handle the logic of moving the pointers. So now the pointers just say, remember, so remember what our actual rule is for this. It's whichever one is lower, that's the one you move, right? Because we can only improve by moving the lower one. So we're going to say, so now if, so here, let me just grab this. Oh, I see why I didn't need to do okay. Oh, I see. I realized this logic actually by default handles ties. I realize this. I inadvertently sort of solved this, but I'll show you in a second. So then I'd say if height left is less than height right, and you can go either way with this. It doesn't really matter. But the point is, if left is less than right, then increment left, right? Left plus equals 1. So if left is lower, move it up. Else, right minus equals 1, right? Because remember, right goes in from this end. So you're decrementing by 1. And by the way, this also handles tiebreakers, right? Because it's arbitrary. So it says you move left, your default is going to be to move right. If it's a tie, or if right is bigger, you move the right in. Otherwise, you move left. So actually, and again, I think from our standpoint, it doesn't really matter which one moves. The point is, if they're tied, you just need one of them to move. So you handle that move. Okay, so that will handle the while loop because eventually that's going to kill the while loop. And so then our overall function, after we've done the loop, right? So break the loop is just to return best. Return best. All right, let me just run this really quickly. Sure it passes my, okay, passes those test cases. Let me submit it. And 86 beats 86.54. And as I see here, there's, and let's see, do they have a, yeah, my memory, not as great, but I mean, that's, I guess in this case, probably fine. But yeah, so again, and this is going to be an O of N runtime because again, right, we just decrement over our list at most once. And um, and then yeah, space complexity is also going to be you're really just storing your pointers and this. So it's sort of a yeah. So space complexity is also pretty, I mean, it's saying I'm not doing great, but all right, any questions on that? All right. So, and again, I want to emphasize this. I do not want you to feel like this is I don't if this is new material, like it should be new material, and don't feel intimidated or nervous about that. Like again, I cannot emphasize this enough. Like this is the first time you're hearing about this. This is, you know, I'm going to give you guys, again, if you want to read up on it, I'm going to give you some material on it. Um, if you want to, and we'll do more examples of this. You know, I'll deliberately try to pick at least the next week or two. We'll do some greedy just to give you guys, again, more of an intuition for that. Because like I said, there are a handful of paradigms when it comes to structuring algorithms. Again, and we've already sort of talked about a few, dynamic programming being one, greedy being another, you know, a handful of like you begin to sort of see these and recognize these patterns, and then you naturally sort of say, oh, this is an example of X. And so it's just kind of a way of thinking about it. So we'll continue to work on that. Because as you saw, like in this instance, there's nothing code wise that's particularly challenging here. It was just thinking about actually how to structure the solution.